So can you see my screen?
Yeah.
Okay. Yeah. Thank you very much for the kind introduction. I think it was a bit like not, I mean, like a bit large, but it is okay. It's morning here in United States, and I hope you are having a good evening there.
Yeah.
So yeah, I would like to start my presentation. And the
Yes.
title of the talk was AI in radiology, but I just wanted to refine it, and then I made it to revealing the unseen, deep learning to detect clinically silent patterns in radiology. So it's me, Devesh Jha. I'm a visiting assistant professor now, but I'll be joining as a tenure track assistant professor at the same university from next fall. So let's start with the motivation. So here I have shown the images of digestive system, which start from mouth to anus. And here you have the organs such as esophagus, stomach, uh, pancreas, liver, gallbladder, small intestine, and large intestine, uh, appendix, rectum, and anus, etc., etc. So we have all these organs, and then so the reason behind showing all this organ is I will talk about all of these. For example, liver, pancreas, uh, uh, and like I think in the next talk I'll mostly talk about large intestine and small intestine. So it is today's talk is mostly related to radiology. So some of these organs, and that's why I think it is important to know. And the good news here is most of the cancer occur in digestive system. For example, HCC, pancreatic cancer, uh, and different pathological lesion occur in the GI tract. Uh, for example, stomach, like gastric cancer, esophagus cancer, colorectal cancer, um, etc. So digestive system is a, you can say, the hotspot of different type of cancer. That's why it is important to know this. And let's move on to the cancer statistic from 2022, because I could not find the 2025 data. So if you see the number of incidents and number of mortality in 2022, lung cancer is the leading cause of the cancer, followed by breast cancer, colorectal cancer, prostate cancer, stomach cancer, liver cancer, and so on. But when you consider mortality, lung cancer is the leading cause of cancer, followed by colorectal cancer, liver cancer, breast cancer, stomach cancer, pancreas cancer, etc. So that's why I think it becomes important for us to study or to improve the detection rate for this kind of cancer. Now, and if you see the trend of both incidence and mortality, so there is no part of the world where you don't have, for example, um, cancer occurring. For example, if you see, considering the mortality, you have a lot of cases in North America and also in Russia. So if you consider India, for example, India is like a safe, considerably safe, and some countries like Nepal or some African countries are considerably safe as compared to the countries like in the North America and uh, other part of the Asia or Europe. Europe is also like hotspot for the colorectal cancer, but it is also like there might be some bias. For example, bias in data collection. For example, if we do not report them, so it might have these kind of influences. So, but from all this information, from all this data, what we can see is Europe and North America are the hotspot for the correct, like all the leading cause of cancer, including colorectal cancer, pancreatic cancer, liver cancer, and so on. And it becomes important to treat this kind of things. So, but why are we studying this kind of cancers? Because early detection can play an important role here. So, for example, this is the statistic that I found from the top 10 cancer, both in terms of incidence and death in the United States. So you can see, if you consider male, prostate cancer is the most leading cause of cancer, followed by lung cancer, colon cancer, urinary bladder cancer, and in female, breast cancer is the leading cause of cancer in the women, followed by lung cancer, colon cancer, and so on. So, but the good news is like some of these cancer have high survival rate if detected early. So this makes early detection very important. For example, breast cancer, colorectal cancer, stomach cancer, etc., have a high survival rate if you treat it on the time. Otherwise, let's say if you find colorectal cancer in stage 4, um, and some kind of cancer like liver cancer, it cannot be treated, but just we can prolong the patient to die. So, or like HCC or liver cirrhosis, etc. So we can just prolong for certain period of time, but there is no such treatment. But there are cancer where there is treatment if we can find it at early stage. So, um, but however, there are some of the clinical challenges in radiology. So the reason behind we are today talking about radiology is there are some of the critical challenges. For example, imaging overload, which means in the hospital you can find, or nowadays like everybody is collecting data and you have a lot of source of data. So this is one of the challenge. So in order to analyze all those data and get information from all those data, it will take a lot of time and clinician, and there will be a lot of like radiologist burnout because of all this dealing with all insurance papers and uh, data, the enormous amount of data that we are getting. And there is also misdiagnosis. If you, for example, if you talk about colorectal cancer, I think when someone does colonoscopy, 1 out of 4, there is miss rate of more than 25%, which means 1 out of 4 patients, there is a miss rate. But you might wonder why there is a, like how we can say there, like someone missed it because it turned into cancer at the later stage. And there is also inter-observer variability, which means inter-observer and intra-observer variability, which means that let's say 2 clinicians might not agree with each other's decision. And there is also time constraint. For example, I was seeing a study. So if somebody takes 5,000 CT scan for 6 organ, it can take them more than 300 years. So, but we as a human, we have limited time, right? So time constraint is another. So which means we have to improve the accuracy. So they are critical, some of the challenge. So you can see the growing amount of data, clinician burnout, etc. And apart from that, there are also things like biases. So biases in radiology and biases in misinterpretation. So there are many factors of cognitive bias, but out of this, I try to find out 2. Like for example, important point. One of them is called satisfaction of search, which means when you search for certain lesion, then you don't want to like go through each and let's say all the Excel slide, or like try to find each of them. And other kind of bias is also unintentional bias, right? In attentional bias, which means missing, finding, hiding in the plain sight due to unexpected lesion or so because of this kind of biases, like these are like human biases, so we need someone like who can help us diagnose and also help us interpret our medical images. So why do we need, for example, AI in radiology? Pattern recognition is a skill. Let's imagine, for example, let us imagine if you have 1 million medical images, a computer vision algorithm or AI algorithm can learn a lot of patterns, hidden patterns from the images, where human cannot learn all those, cannot go through that 1 million images. Efficiency, so AI can help us boost efficiency and speed up and also scale, right? The other one is precision. So it will help us reduce the human error, like we have discussed previously. And then quantitative imaging, which means extracting a hidden radiomics feature, like or extracting hidden features from the images that are like that as a human we cannot find it out. So you can see, like for example, this is the image showing input image, AI detection, and radiologist. So which means like we are talking about like a human in the loop. Radiologists make decision, but can take a second opinion from clinician. So now let's move on to like a project. So we say from raw data to knowledge. Let us consider this is a Google or Apple map. So this is a raw data, and this is a geospatial. For example, it can be geospatial data by satellite, drones, etc. So this can be calculated. Now, from this, like if somebody annotate this kind of images or these regions, then maybe we can make information out of it. So this is my university map. So for example, you can annotate a road, lane, sign, region of interest, or a point of interest, etc. from it. Now this becomes information. Then once you have information, then from this information you can gain knowledge. For example, distance between one department to the other department. So and use it for route optimization, and also like use it for prediction, traffic, etc., etc. So and once you have all this, for example, once you have data, you convert it into information and again get information out of it. Now you can use it for a lot of downstream tasks. Like for example, Apple Map is being used by Starbucks to locate their each store. DuckDuckGo, like there maybe in the Zillow, it is used for real estate. Snapchat uses Apple Map. So similarly, what I wanted to mean is when we have raw data from the hospital, we can make information out of it. And once we have information, this is the knowledge. I think there is some, this is knowledge. And once we have the knowledge, we can use it for multiple applications. So now we are trying to map this like Apple Map for the healthcare. So this is our raw data from the hospital that we get from our collaborators. From the images, from the raw data, we convert it into useful information. Once we have useful or information, then we can discover knowledge from it. For example, here hepatology, or it could be cirrhosis. Then you can use it for example, treatment like radiation therapy treatment and so on. So you once you have the knowledge, you can do post operation like radiation therapy if needed, right? And once you have this knowledge, you can use it for many downstream tasks, like for multiple applications. So so this is an example of radiation therapy. So once you have the knowledge, you can have, for example, you can delineate what is the gross tumor volume, what is the clinical target volume, and planning tumor volume, so on. So usually medical physicists and doctors, they do all of this. And this is another part of the research, but AI can also play an important role in dose optimization and so on. So these are like different downstream tasks. Once you have the data, you can do it. And then like Apple did for the chart of the world, we are trying to map the human body. So the first step, but there are different challenges in medical community. One of them is data limitation. Like you already know, there is availability of small test data, data bias, data quality issue, because it's very difficult to find like the latest data. We have been collecting a lot of data and we have this experience. Now again, you have evaluation issue. For example, most of the paper, they use only few metrics or one metrics on fair comparison. Everybody say they are the best, but like there is issue with the comparison. And then there are issues such as like noise and artifact, adversarial effect. For example, when you inject a small noise inside the medical image, like to the clinician, it might, or to the human eye, we cannot say that there is a noise or there is an injection of noise, but it's a computer vision or like algorithm can detect it, and it has the influence on the result, which we have some experiment for this, so we can see. So there are different issue and different challenges in medical imaging, and we are trying to address these, for example, out of distribution or domain shift. For example, let's say if I collect data from Turkey or United States and develop an algorithm over that, that might not work for a patient in India. So uh, because of different factors. So, and at some point of time, like there can be also issues such as like what are the device they are using for data collection. So for example, what type of scanner, like whether it is 1.5 Tesla or like what kind of scanner, or what is the gold standard. Different countries, they use different standards. So there are different things. So these are some of the challenges. And in this talk, like I mentioned, I think we'll mostly cover about, talk about liver, pancreas, spleen, some of the application of the radiology, like we can touch lungs and heart as well. But there are other organ in the radiology that I think will not cover, such as kidney, gallbladder, GI tract, prostate, etc. So these are the part of the radiology, but we cannot, we are not going to cover. But if you see like lungs, there are different imaging modality. You can check from here. Some of the areas, there has been already like some impact, but some of the areas like pancreas, I think there is moderate because of the challenging nature of pancreas, spleen, even liver cirrhosis is like unsolved and like not explored much. So there are different types of organ that we can look through. So, and we try to do this um, through this Med Atlas X initiative. This is a holistic approach to radiology. So we try to achieve this goal with 3 steps. One, we say data curation. Other one is diagnosis, and third one is benchmarking. By data curation, like we mean the collection of a multi-center, high-quality data set, and we have like expert level annotation. And by disease diagnosis, like we talk about early diagnosis and such as early diagnosis and many applications such as disease classification, segmentation, and real-time decision making. It is not really important in radiology, but mostly, for example, endoscopy and so on. And by benchmarking, we mean fair comparison and OOD testing, and like multi-center or like a cross data set evaluation testing. So my talk is mostly in 3 parts. At first, I'll talk about data curation, our data curation effort, and that we made it publicly available. Then I'll move to different algorithm, and then how I'll try to show how we achieve this goal, or how we are in the stage of achieving this goal. So let's talk about some of our open access data set. So this is a general figure for how to collect data set. So if you see, the first step that the doctor does is they write a proposal. Then you need to get ethical approval, get permission from the hospital, also permission from the patient, right? And you have to anonymize the data, then you can collect data. And then basically data inspector checks whether it is handled anonymously or not. Then you get annotation and you can label the data, and quality assurance is done. Certain documentation like meta information collection and so on, like there are different things that are done, like in addition to for example, preparing GitHub page, or like trying to split it into train, test, and valid. So if you have also language like a question answering kind of data set, maybe you'd like to have that. Then you take all the ethical and legal compliances, and you can release the data. So this is like a general process to make any data set open source or to collect the data. Now let's move on to our effort. So this is a current work that was published in Nature Scientific Data just a week back. So we call this is a cirrhosis MRI 600 plus, large scale MRI collection and segmentation of cirrhotic liver. So here is some information about the data set. Um, Here we have both T1 weighted and T2 weighted images. So you can see like the difference between T1 weighted and T2 weighted images is like here you have more contrast, and here you can see the fluid. So you can see images from like mild to moderate liver cirrhosis. So we collect this data set. It has a total of 628 scan from 339 patients. So you might be wondering, if it is only 339 patients, then how come you have 628? So basically it is into two, T1 and T2. We try to provide the corresponding T1 and T2, but some of them are corrupted. So we don't have information related to them. For example, if they are corrupted, so we do not include them. So so in total there are 310 T1 weighted and 318 T2 weighted images, around 40,000 slices. So we use this scanner as 1.5 Tesla and 3 Tesla, and data set can be found here. And this is my website, and one can download data from here. So let's move on to T1 weighted MRI dataset. T1 weighted dataset, like I think, so this is like our raw image, and then basically we annotate with the help of expert radiologist, and also we try to take the help of AI. Otherwise, it is like very difficult to annotate it manually. So T1 weighted is better at anatomical details. Like you can see it here. It shows morphological changes and detect contrast enhanced SCC. So this is like especially useful for to find out the anatomical detail. But you have T2, which is basically used for finding the fibrosis tissue, or what you call fluid. Here T2 weighted, you have the higher contrast. So for detecting fibrotic tissue, edema, and certain abnormalities. So because here the fluid appears, water appears as bright, and fat appears as dark. Whereas for T1 weighted, water appears as dark, and fat appears as bright. So and this is our annotation protocol. So you have raw data, we annotate it and make it like useful for our tasks. So let's move on to our annotation workflow. First of all, we get DICOM image from the hospital, then we convert it into NIPT format, and then we have used ITK snap tool. So we try to label each slice from the 3D, each volumetric slice. So usually why we convert from DICOM to NIPT is like we can reduce the size, and NIPT is very easy to handle. And then we also we also anonymize the data, meaning we remove all the patient information, and also for example whether they are male, female, and all the identifiers when we release the data. So we do this during our annotation protocol. And then I think when we collected this data, the first thing what we did, because liver is very easy to segment, and we use like we train AI algorithm, and then we give this output of the AI algorithm to the doctor, because now they can easily crop or max out some certain part of the region that is not, for example, liver tissue. So and it makes our life pretty easy, because otherwise if we try to annotate it pixel wise, it is really difficult. So let's move on to the data set. So these are the data set available in the community, and we release the new data set. So there is no data set related to liver cirrhosis, and we are the first one to release this data set. So once we release dataset, we also do some experiment so that community can make it, like we call it AI ready data, and then so that community can use it. So here you can see, like we compare with the state of the art algorithm, and this is also our algorithm, and then Synergy Net 3D. So we get the better result. But the goal here is to just benchmark so that other people in the community can use it and improve the algorithm. Similarly, this is the benchmarking on T2 weighted data set. So we got pretty good result with like around 83 um, of mean IU and 86% dice coefficient. So these are quite impressive, but and then we also do some qualitative results. So from here you can see, for example, this is T1 weighted modality and this is T2 weighted modality. So here this example shows the mild case and this is severe cases. So if you check the mild cases, so we try to compare with the algorithms such as attention unit, trans unit, NN unit, and this is our algorithm. So you can see, for example, this is the ground truth. So this is like gold standard. So our algorithm is quite good, whereas they miss some kind of, there is kind of like you can say um, what we call under segmentation, right? But if you see severe cases, so I think none of the algorithm is performing good, but somehow our algorithm is performing better than other. But I think there is a lot of work to be done for severe kind of like severe cirrhosis. Same for the T2 modality. So these are like this is one work. Then once we have this segmentation now in the clinic, what we do is we try to grade them, or the doctors try to grade them. So segmentation in itself is not enough. Then we did another work. This is also recently accepted at EMBC, I think Denmark this year. So what we do is like stage. For example, we try to grade this data into mild, moderate, and severe for both T1 weighted and T2 weighted. Uh, so you can see here like this, for example, and here also we provide, because reviewer asks us to provide like age information and gender information. So we also provide this age information, gender information, and also radiological evaluation. For example, 3, 2, 1, etc. So this is for T1, T2, T1 and T2 paired, and then here 1 refers to male and female, and then 1 refers to mild, moderate, and severe. So 1, 2, and 3 refers to this. So one can use this also for classification tasks, because this is the ultimate goal, so that you can, let's say, discover the pattern. Like you can whether say it is a mild or early stage or severe cirrhosis. So we do some benchmarking here as well. So here we compare with the deep learning based approach, and then I think this is with classical machine learning like decision tree, random forest, etc. So of course, for example, Mamba based approach, we also use Mamba based approach, but it seems PBT based approach is better here, like transformer based Bayesian transformer, pyramid Bayesian transformer is better here. So we do this kind of benchmarking so that other people in the community can use this data set. Now let's move on to our second data set, and we call it peripancreatic edema data set. So the first slide that I showed you, so I said like we'll talk about pancreas. So here we are talking about pancreas. So this is a pancreas, and it is one of the most, like it is the most challenging organ to segment. So here, peripancreatic means it is a condition where fluid accumulates in the tissue surrounding the pancreas. So this is like our doctor tried to find out the layer, like this layer, out layer, so that like early treatment is possible. So it is an indicator of disease progression. So it is like fluid, like here fluid accumulates and helps to determine pancreatic severity. So this is another data set, and nobody has released such kind of data set. So last year we released this data set, and it consists of 255 CT scan from 255 patients, and there are like we have with edema and without edema, like healthy patient. So we released it data set, and again the procedure is same. So the procedure is to annotate this thing, but I think liver is quite easy if you compare with the pancreas, because it is really difficult to annotate pancreas. So we made this data set open access, and even the previous data set open access, anybody can use it for classification tasks. And then we also did some benchmarking. So first of all, we got this data set from the hospital. Then what we used was, this is one of the algorithms from our lab. So we trained uh, we use this algorithm to generate some labels. So once the label is generated, now what we do is, like, we extract the ROI, like for example, the pancreas. Now we use the ROI, send the ROIs to like a two-stage approach, we can say. One is for radiomics analysis and another to the deep learning. And we try to run like classical machine learning or versus deep learning and see which one performs best, and or benchmark on both of the classes. So the goal here is to find whether there is presence of edema or no, right? Uh, so these are some of the result. So here, Swin uh, Tiny is the winner. So we try to calculate some of this like precision, recall, etc. We have pretty good result. Now let's move on to the third data set, and this is the last data set today I'll talk about. So we call it PanSec data set. So it is a large scale data set from 5 different institutes. We collaborated with New York University, Mayo Clinic, Northwestern, Allegheny, and Mayo Clinic. So we released this data set. And then, like I mentioned, pancreas is one of the most challenging organ and very difficult to segment. And it is also challenging because it is irregular. There is low contrast and boundaries is ambiguous. And also, like, the size of this thing is pancreas is small. So the annotation, like how we do, is the same. So you can see for both T1 and T2 weighted images how we annotate pancreas. The data set is made available, and like we showed, there are 5 centers. We try to do some try to evaluate the result for each of the centers, got some score. And by the way, like here, I did not want to explain a lot about this one, our algorithm, but I think for pancreas, I'm sure some of you are like expert in radiologists. So if you know, like none of the team has reached a score of 80, more than 80, or like I think the benchmarking was something like 75, 76, but we we are the first team to make it 85 or 86, like 18 average of something like more than 80. So this is and we made like it is a big news. And also on this like large scale data set, there was no team to achieve this scores like a dice coefficient of 86. Because this organ is very challenging, and also there is disagreement within the doctors. So these are some of the open access data set that I release, and one can find it out from my slide. And like usually I use OSF, open source open source foundation. I don't know what is the full form, but I think it is mostly used for open sourcing the data, and also open source framework. So open sourcing the data, and then I think it mostly come from Europe. So some of our work has been featured by Stanford AI Bench Index. So always like Stanford AI report from 2022 to 2024, they featured our work. But this year, they did not feature because I think mostly they talk mostly about LLMs, less about LVM this time. Or yeah, so, and also they talk more about like because of all this like talk about reasoning model and all those innovation like DeepSeek and so on. So now I think there is a need for novel architecture. But why do we need novel architecture? Because for example, let's say if unit was sufficient, then maybe would not try to develop a new architecture. Maybe just try to develop new data set and then use vanilla unit or the algorithm that are already existing in the community. But this is because like the existing algorithm, they are not sufficient, or they are not efficient enough, especially for the small organs, and they cannot handle variable complex organ, etc. So, and there are same problem like I mentioned previously, like issues with like poor generalization, some organ like small organ are not detected, and ages are ignored, and so on. So now let's move on to the architecture. Um, our architecture. So the first architecture that I would like to talk is MDNet. We call it multi-decoder network for abdominal CT organ segmentation. We published this at ICAS this year. It was recently published. So here is the architecture we propose. You have the CT image. It passes through MIT B2 encoder. Um, where you can extract like multi-scale features at different scale, like for example F1, F2, F3, and F4. So here this is like our innovation. So we call it, now these features are passed to dilation convolution block and MSFED block. I think it is called multi-scale feature uh, extraction uh, dilation block, something I can recall now. So this block. So here, um, if you see, so the main goal, okay, yes. So the main intuition behind development of this algorithm is like the model can learn iteratively. For example, you can see our segmentation here, but okay, this is wrong here. I think it should be here. So you can see our segmentation here. So this is like multiple decoder from the name, our segmentation here, but we are trying to remove this our segmentation. And it finally, you can see like the model is not segmenting, just segmenting liver, but not the spleen. So this is wrong here, this is wrong here. So here, like we have 3 decoder in the architecture. And okay, so now you have the feature extracted at multiple scale. Now this F1 is passed through dilated convolution block, where you have for example, where you can retain meaningful information such as context, and also you can have spatial and meaningful information, and which is passed through the decoder block. So this is the uh, component of the decoder block. The input is passed through transpose convolution. Here you can upsample to match the uh, scale, like feature of the encoder, and then which is concatenated through skip connection. You have residual block to ease the training, and then residual block helps you to like 2 residual block. So it helps the training, and also it helps to it helps like skip connection here helps in better information propagation. And then you get this output, and this output like is passed through the decoder block, and then you get like output 1. Now here what we do is the output 1 act as an input to the another decoder, and we have marks attention block here, where we marks like this is the architecture of the marks attention block. So here you have both foreground and background, and then we do kind of like we employ 3x3 convolution, concatenate it, and get the concatenated output. So basically here we try to force the model to learn most important features. So this is passed through marks attention block and the output of the decoder as well. So now here the model is trying to learn iteratively, step by step, and we do the same for this one. And where now we have, for example, the output from decoder 2 is the input to the output, this architecture, like decoder 3. And again, we pass through like a series of mass attention block and decoder block, and we try to improve it. But you might have question like, why don't we use decoder 4, decoder 5, and so on? Because here what we do, like we also have to accumulate for the complexity. So that's why we do not use more. And I think this was the optimum. So let's see the result. So we try to do it for 2 organ. One of them is liver and another is spleen. So if we compare with algorithms such as G-cascade, as high farmer, etc., so our method was quite accurate. And here you can see under segmentation from the G-cascade, but our algorithm is better than the state-of-the-art algorithm. And this is the heat map showing how our model learns iteratively. Now let's move on to some of the quantitative result, this quantitative result. So we get a very good score for the liver. One thing I wanted to mention about the liver is, like, liver is a large organ. So even if you get, let's say, even if you segment everything, you get more than 50%. So getting a high score for liver is not a big deal, but yeah, so we get high score for the liver. Um, and our method is best if you compare with like G Cascade and so on. So, and we do also same for spleen data set, and then we also got almost around 95% this one. And then we try to do some ablation study to understand the impact of so each decoder, for example. So you can see decoder 3 has advantage over two other decoder. So these are some of the result for the liver. This is the result for the spleen. So you can see our model is quite good. It's segmenting these organs. Now let's move on to another architecture that we call SynergyNet. We published this in uh, last year in WACB. So SynergyNet, if you look at SynergyNet, so this is like for example, traditional work. They use, for example, continuous feature is passed through the transformer MSA layer, multi-scale attention layer, and then passed through feed forward. And this is how like traditional approach work. But what we do here is we introduce this module, this conf module, and we fuse them, and we also introduce this refinement module. And here, instead of continuous, we also try to integrate like pass discrete code, and then try to show improvement over the other state of the art. So here the input image is passed to the encoder, where you get pre-quantized value like ZCon, I think. Yes, that now it is passed. Now you have a code book here. So I think you understand code book. So let's say you have a quantizer here where you calculate the distance. Yeah, calculate the distance and try to like perform argmin here and see match, for example, this value, continuous value. Let's say if the value is 0.6, for example, and if the value in the code book we have 0.64, which is like indexed from the code book. So maybe you take this value, like the one which is nearest. So yeah, you match with the code book, and then now we have another module such as DixCon, where here we have query key and value, and we pass it to the soft attention, and we got some like attuned feature or like boosted features, improved feature map. But this one we fuse it with the refinement module. The refinement module here, this is like a hard attention. So we get we try to fuse it and then pass it through the decoder. And here, like one thing to note is like we have two loss function. One is this LSEG and LQuant. So this is what we use during training the network. So and we get the results. So I think we did it with multiple organ segmentation. There is a data called Synapse dataset. So we talk about the heart. So here is the aorta, gallbladder, kidney, liver, pancreas. So these are like multi-organ segmentation dataset, and we compare with different architecture like CNN-based, transformer-based, etc. And we get the better score for this one, multi-organ segmentation for each of the organ. And then we also perform on cardiac segmentation tasks. So we also got better score here, or competitive score here. I think, yeah, a little bit better score here on this data set. Now, we also did it on another data set, skin lesion segmentation data set. So we also got like this 3 is like all of us are our model. So we got best score, and this is the result for multi-organ segmentation. So this is liver, these are spleen. I cannot see pancreas. So here are different, like for example, gallbladder, kidney, kidney left, right, liver, pancreas, spleen, stomach, and this is iota, like that we saw. So our model is quite good. And if you see with like compare with the other architecture, so you can see some under segmentation, but here we saw that our model is quite robust as compared to other architecture. And this is another result for skin lesion segmentation, where we saw that our model, like this is ground truth, which is like a gold standard. Then we try to compare with the other architecture in the literature, and we say, okay, our architecture is better. So we also do, like, for example, brain tumor, and then we saw this is like more like ablation. So what is the number of code book, like what is the optimal value? So with the k equal to 1024, we say that this is we get better score. Now let's move on to our another architecture. So this is the third architecture. We call it PVT farmer. So this is somewhat similar to the previous architecture, we can say. So instead of MIT B2 encoder, we use PVT B2, and here we do like, for example, encoder extract hierarchical feature maps at like 64 by 64, 32 by 32, and 16 by 16, and these are like at 3 different scale. So this is like feature extraction, like you extract low, high, and level features, and then you pass it through up block. And here I think we should have up block, yes. So here, like in the up block, we have input is passed through upsampling. Like here, I think we use bilinear interpolation and pass it through the residual block, so that we take the advantage of this residual unit to improve the model performance, or like to suppress the irrelevant feature and to focus on the relevant features. These are passed through up block, and then here is the decoder. Now we pass this through decoder block, and again we use up block, and then concatenate all of this and pass through. Like here we do one by one plus bn. This is just to like what we call to make it less computationally efficient, and we again concatenate it and then pass it through the residual block, and then con2d sigmoid, and then we get the prediction. And we compared this with other architecture in the literature, and we get a better score for CT. So these are some of the qualitative results. So our method is quite good, and I think this work was published last year or in ISPI. Now let's move on to our fourth work, that we call it diff boost, enhancing medical image segmentation by text guided diffusion model. So the goal here in this work is to develop a novel data augmentation technique that works better than other architectures. So let's see. So deep boost, here we have 3 stages. One, we have pre-training stage, another is fine-tuning stage, and third one is downstream tasks. So here, what we say is training a diffusion model on comprehensive radiology imaging dataset, RED-ImageNet. So model, so during pre-training, we train on RED-ImageNet dataset. It is a large scale dataset, and then we can extract, for example, age, shape, etc. And we also use like text prompt to train the control net, and then we get synthesized image. So basically here we can get during pre-training, we can get like what you say, general information about all types of images. And now the second stage is like fine tuning, where we add the marks, and then we try to use it for the specialized tasks, and we get the synthesized image. And at last, we use it for different downstream tasks for image generation. So yeah, this is the 3 stages. We call it like fine-tune, pre-train, control net, and then for the segmenter, you can use whatever algorithm you want, like UNet or other architecture. So if you see here, this is the original image from RED-ImageNet. So this is from MR hip, CT, MR ankle, MR brain, ultrasound thyroid, MR spine, etc. So this is like ACE, and this is one method, pix to pix, and this is our method. So image generated by our method is quite better as compared to pix to pix method. And these are different sample generated. So these are original images and different samples generated. So by our method. Now these are like different samples generated, different hyperparameters. So alpha equal to 0.0 means like all patches come from synthetic image. Alpha equal to 1. So I think we know this. All patches come from original image, and between 0 to 1 means like it has both the feature from a real image and the generated image. So here are some of the results. So when we compare to pix method, so I think our one is quite better as compared to the other one. This method, this technique, and we try to compare with all the data augmentation technique, like for example, random contrast, random gamma brightness, random noise, etc., etc. And we saw that we have the improvement over the other for different like tasks such as prostate, spleen, breast cancer, etc. So these are the results for different method, and from here you can see that deep boost is better if you compare with, like, let's say random rotate. Here you have kind of over segmentation, so deep boost is better than others if you compare baseline and with the other architecture. So here we show the influence of task coefficient versus augmentation ratio. And here you can see like whatever architecture used, we call it influence of a backbone architecture on segmentation result. Deep boost achieve promising and consistent improvement. So you can see like if you use deep boost, for example, the performance is improved for each of the architecture like unit, crystal unit, attention unit, etc., etc. And beside all this work, we also do like work on ethics, try to so that community is aware, because once we release like many data set, we call it trusted data set, right? So we also do some work on ethics, but at the same time we try to do some experiment. So like I mentioned previously about the adversarial robustness. So this is the clean image coming from the hospital, and this is the ground truth delineated by the clinician, and this is the clean prediction by the unit. So, and let's say here we inject a noise like a Gaussian noise or something. So this is the adversarial image, and when you compare this image and this image, and we showed it to the doctor, all these images, and then we asked them to say whether it is a real image or fake image, then I think they were not able to identify. And as a human, it is very difficult to say distinguish between real and fake image. But you can see the architecture, like algorithm is here performing miserably low. So from here you can see the algorithm is quite smart, and they can say they can unreveal the hidden patterns, unlike a human being. So I think we have to build algorithm that is robust to the noise. And also I think we have to think about building a data set that is also robust to noise and artifacts. So we have to consider this kind of things. So, and okay, so when talking about generative AI, so nowadays I see a lot of people, they have been using like, for example, generating images using ChatGPT, or also because now previously the image generated by ChatGPT, or like let's say or other, especially ChatGPT, it was like not good, but now I think it can generate quite a realistic image. The first image I used for my slide is also generated from ChatGPT. And what they say is when you use like original image plus synthetic generated image in the training data set, you can boost the performance. And other thing that people mostly talk, like all of us, we wonder what is the optimum amount of the data set, because we that we need to train AI, because nowadays there is something called like we say more data is better. However, so I think we did some experiment, and we are in the stage of doing some experiment to say like what is the optimum size of the data set, whether the size, like I think I remember one study done by John Hopkins, they say They first did some experiment on 5,000 CT images, and what they reveal is, um, okay, so they got, let's say, 90%, and now instead of upscaling, they try to down scale it. So let's say they try to test it with 1,000 images, and what is the uh, performance lost, like when you compare 1,000 with 5,000 images. So the thing is, like, we have to think about whether we need more data, or we need more like fine tuning, uh, or like yes, more fine tuning. So we did some experiment here, um, but this is not related to radiology. This is related to endoscopy, and we got opposite results. So when the algorithm was trained on real data set, you can see we got an accuracy of around like something in between 65 and above, box plot of this much. But when we use real data and synthetically generated image from control net, we lost the performance. So maybe it works for some type of data and it does not work for other type of data. So I think it is mostly like more like a research. So, and also when you generate, let's say these are realistic images, so there is also some text. So here also text is generated, and this sometimes this text might reveal something that you don't want to reveal it, so you want to anonymize it. And sometimes this also deteriorate the performance of the model. So I think uh, so we have seen some result that is really working, like when you generate more data, so that one thing that you can have is like you don't need, let's say, even we generated like our data augmentation technique we showed, we can generate as many as data we want, and there is no privacy concern when we generate data, right? So also, I think it is mostly important for generating samples such as like real rare cases, or that we do not find in daily life. So we could generate those kind of images. But like this is an ongoing research. So whether to conclude like whether it helps or not, depending upon the modality. But in general, I think it is useful. Okay, so even what we did was like for this one generated using injecting noise, or one generated using a deep boost algorithm. We showed it to our clinician, and usually young clinician where they were not able to identify whether it is real or synthetic, which means like they're more like a random guess. So like their confidence was more like a random guess. So I think we can also use this kind of data set to train uh, train uh, like new clinicians as well, and we can use it for other purpose as well. But this is like ongoing research, and then I think we have to penetrate under this area. And one thing is like now I think at some point of time everybody is collecting data, so everybody will have access to data. um, but again, when you talk about annotation, like maybe I talk a bit quickly about data annotation and so on. So from our experience, I think it is a very tedious job, and then it is very difficult to release data set. So like my suggestion for like new engineers would be to focus on algorithm, like develop algorithm that could maybe um, automate the process, or maybe generate better artificial segmentation marks that we can use. Otherwise, like generating uh, a lot of data, or like building data, it would take a lot of time, and then I'm not sure how much helpful it is. So we have been doing this. So my recommendation for the new scientist would be to focus more on algorithm part, like efficient algorithm. And yes, so okay, let's move on to the other part of the research. So other part is like one of the thing what we do is like, okay, let's say you now you segment it, now you have the knowledge. So what next? So we have been using AI for the diagnosis, but I think we also now we are trying to use the AI for the treatment side, where we say whether the algorithm respond to the therapy or no, so that one can get personalized care, or like at least they can know even after therapy some patient will die, so we have some information and we can better treat them. So we propose some algorithm, but I think considering time, I think I'll go a bit fast. So we also have like, beside this, we work on the ethical framework for foundational model, like some conceptual paper on ethics, which I'll not talk. Uh, and apart from that, one task that we have been doing is like denoising CT. For example, this is a gold standard image, and this is a gold standard, and you need to have 100 kV energy to produce this kind of images. But at the same time, this is 40 kV image, and it is a noisy image. So our goal is to develop something algorithm that is as good as this image, so that we can protect from a lot of radiation, and then that is really useful in the clinic. So yeah, these are some of the features. Then like this is the algorithm that we use, and we showed it to the doctor, but it is already done, so maybe not talk about a lot. City Farmer. So we convert the image into patches, like we do tokenization, detokenization, and like downsampling, upsampling kind of thing. And we are in the initial stage, but this dual energy CT, I think there is no research from the computational side on this kind of images, and this has potential to really change clinic. But at the same time, I think there has been some confusion uh, because yeah, so with the clinician, because they say, okay, we already have this image, so why do we need this image, and so on. So otherwise it is very difficult to reconstruct the same image. So yeah, so but these are some of the publicly available images, and we performed some experiment using red CNN, and we showed it to our doctor, and they said, okay, you are able to remove the noise from or your from the input image, or your image is better than the previous image. So these are some of the result on quarter dose, full dose. So this is quarter dose, this is result. So the goal is to make it like a full dose. And if you check a PSNR, SSIM, I think our result is quite good as compared to, so yeah, it is compared to the other. And apart from that, we also do work on such as building novel activation function, but I would not go a lot of detail into it. But this was published in MICAI last year. So we try to do like, for example, develop new activation function where we compare with the other existing activation function, and we show that our algorithm is better, and it works both for segmentation and classification tasks. And this is kind of our annotation protocol. Like we have labeled image. Usually we use a trained model. Like I said, for example, I think you might be aware of total segmenter and then algorithm like this. So which are like good for segmenting all those 136 anatomical structure. But again, if we compare with our algorithm, like on serous MRI, I think they are quite, they are not up to the mark now. But we use a trained model. This is poly, but let's consider it is a radiology. So we use trained model, and then on the on-label images, and we separate, and then we use human annotator, like this is like a human annotator. So yeah, these are the some images, like once you build the pipeline, for example, like a Apple map, once you build Apple map that is functional, then you can build many things out of it. Like you can use it for many third-party app. But the first thing that we need to have is like data set that we have been working hard to make it open access under non-commercial license, and sometimes even we like donate it to industry, because our ultimate goal is to make a solution out of it. And also, once we have data set, I think we also organize competition challenges and workshop, so that we can get crowdsourcing based of the based kind of solution. So these are like different applications. So these are kind of downstream tasks. And now I would also like to highlight about one of our work. Currently, we are working on dental X-ray as well. So this is not a radiology, but like there is some overlap with radiology. So the goal here is to, for example, detect dental anomalies like PAL, caries, and so on. And we use algorithms. So we are in the process of annotating the data set. So what I would like to say to new researchers, like stay tuned. I think we might release both like segmentation level data set and question answering level data set for this one. So we have published a lot of data set, and then we also try to make our code open access, so that people in the community can make use of this code and reproduce it, and then build better algorithm than ours. And this is like a made at last summary. So we presented, like we design architecture, a different architecture like MDNet, PBT Farmer, Deep Boost, etc. And we release standardized benchmark data set like PenSync data, CIRA MRI data, CIRA MRI 600 plus data, peripancreatic data. And then we show deployment roadmap. So once we have data, we have better algorithm. I think we can integrate it, or think it to integrate into clinic, but you need a close collaboration between radiologists and computer scientists. And also, I think now we are moving more into self-supervised, which I did not present, and semi-supervised kind of approach, because like with supervised learning, it is very difficult to annotate all those data set, and you need to keep record of all the version of the data set. And so, yeah, I think it's very tedious. So yeah, I think that's all about me. Thank you very much for listening. I would be happy to take any if you have any question.
Yeah. Thank you, Dr. Deves, for sharing your experience with us, right? How you have designed the data set and the model you have designed. And there are also some important things we have mentioned, right? I mean, regarding medical imaging, but it's basically in the radiology.
Yes, yeah, we also have some work on report, but yeah, I did not present this
Yeah,
one.
I think you have also another lecture in our FTP where probably you will be focusing on gastrointestinal disease and all. So there also you can, so I mean the other data sets which are very popular, right? I mean, which people have been using since last couple of years. I mean, it has been a benchmark data set, couple of data sets he designed. I mean, emails as well as video data set you will be also talking about. So you can work on either image or video data set. That's a huge contribution towards the research community. Yeah, participants, if you are having any queries, Dr. Deves will happy to take it. We can wait. Actually, they cannot unmute their mic and directly interact with us. They can only write their queries in the chat box.
Okay.
So you can see, yeah, there are questions.
Yeah, I can see how can class imbalance between adenomas and other polyp types bias model prediction in real world application. Yeah, so we try to, and other polyp. Okay, could you recommend suitable open source tools for working with 3D Nifty? So I think for this Nifty images, I think you can try total segmenter, and there is also MRI segmenter. And for this one, like how can you handle class imbalance between adenomas and other type of polyp? Maybe I think I'll talk about this. I have a slide on this maybe tomorrow.
Yeah. Any other questions? Yeah, there's.
But in general, talking about the adenomas, I think Yeah, I think like polyps such as adenoma, sessile polyp or serrated polyp. So these are challenging, but also very difficult to find it out. So we release something like capture sessile, where we have some adenomas because these have the chances to grow it into cancer. Um, so balancing, I think this is a tricky question. Like there are some like what we have been doing, like maybe try to balance out the data set or use some, for example, focal loss or so on to balance, or how you can do. So this is, yeah, this is tricky. We can only say when we have like more, like for example how like, okay, so one thing what you can do is like I showed, like we can develop novel data augmentation technique as well, that we showed for this one, and deep boost. And then what we can do is, let's say, yeah, develop novel data augmentation technique especially for those kind of images. And like I mentioned, in the clinic, it is like it might not be direct useful, like the synthetic image might not be direct useful for uh, like when you are working on deployment, but you can still use it for training, right? And check whether it is improving your performance of the model. But at the same time, we also worry about like, okay, so how much diverse, like I said, alpha equal to 0.5. So how much diverse you want? So like otherwise, sometime uh, the model might be overfitted, and which might deteriorate the performance of the model. Yeah. And at some point of time, I think even overfitting is good because we want model to overfit. Let's say if we just generate adenomas, because let's say, just think, I think I'll talk tomorrow. So
Yeah.
if you want, you can have something like, you can give a prompt, generate me adenomas, and then you have one normal image. You just paste adenomas. So sometimes the background might be different, but generating adenomas, like because the size of the adenoma is very small, so generating adenomas over those area um, could be beneficial. So maybe we want to generate, like you can force model to generate those kind of images. So I think I'll talk about it tomorrow more. Can you suggest open source data set for lung CT and MRI, same patient? So I think lung CT and MRI. So there is MST data set one can use. And then I have released a lot of data set like on liver, not on lung, but liver. Maybe you can use that. It is open access. And then, like I mentioned, peripancreatic edema, nobody has done before. So you can develop a tool. And I had a lot of like ticks. So maybe lung is close to getting FDA approval, or there is already a lot of work done on lung. So maybe you would like to switch to challenging organ like pancreas, which is not much explored. So this is my suggestion. Uh, any more questions? So I think we have to try to find out the niche, like what has not been done before. Like I showed, for example, dentistry, like it is almost unexplored. So if we can develop something like dental GPT, I think that will be useful for everyone. So instead of doing overlapping research, I think we have to try to unlock or try to discover the areas that are not resolved, which is usually difficult because it is more like a, like I saw Apple map. Once you build a map, you can develop whatever.
Yeah.
Any more questions?
Uh, yeah, I think there are no other questions. Right?
Okay.
Most all questions have been answered.
Okay.
But I mean, most of the work actually Dr. Daves has shown to you are open access, right? His code, his data, everything is open access.
Yeah.
So I mean, after accessing the data, if you want to interact with him, I mean, you can just directly drop an email to him. So, I
Yeah.
mean,
Yeah. Also, one thing I wanted to mention, I think next year I'll be hiring a PhD student. So maybe if you'd like to join my group, you can join my group. Other thing, if you want to collaborate on some of these areas, or you have your own idea, you want to work on radiation therapy, for example, I think like, for example, dose prediction. So these are real clinical problem. So there are a lot of work on early diagnosis, but no work on treatment side. So I think we should more penetrate on the treatment side. So because that has more clinical application. So yeah, if you want to work on those area, maybe you can feel free to reach me.
so I think there are no other questions. Okay, so let us join my hand to thank Dr. Devesh uh, for his wonderful talk and sharing his expertise, how to develop the data set, how they've consulted with the doctors, where they need the help of the doctors, and how to overcome the problems, whatever they faced. And they've also, I think, developed so many algorithms he has shown to us. So thank you, Dr. Deves, for joining us today. So you'll be having one more talk tomorrow, but I think
Yeah.
it's early morning at US, so I know it's very difficult for you because maybe I think we talked few hours before, right?
Yeah.
So I don't